Okay, so we would like to do the worksheet for week 8 and also the review sheet. So let's begin with the review of differentiation and integration. So we would like to take the derivative of the function 7x squared plus 1 over x cubed plus x plus 1. And of course, this is going to be the derivative of the top, which is 14x times the bottom, which is x cubed plus x plus 1, minus the top times the derivative of the bottom, all squared. Because after all, remember that the derivative of f over g is f prime times g minus fg prime over g squared. Okay? And secondly, we want to take the derivative of secant of e to the x. Now we can apply the chain rule. We just need to identify the inner function, which is e to the x, and think of this as secant of y, if you like. The derivative of secant of y is tangent of y times secant of y. I never write y, I write directly e to the x. And then I have to multiply by the derivative of what I called y, meaning e to the x here. And that's the derivative. Then I have an integration. I have the integration of from 0 to 1 of x squared plus 1. Here we need to recall that the derivative of the arctangent is precisely 1 over x squared plus 1, which means that the antiderivative of 1 over x squared plus 1 will be the arctangent. And we want it from 0 to 1, which means that we will get arctangent of 1 minus arctangent of 0. And we need to ask ourselves, what is the arc whose tangent is 1? And the answer is pi over 4 minus 0. So altogether we get pi over 4. Finally, we have an improper integral from 1 to infinity of 1 over x squared. We think of this as a limit. The limit as b tends to infinity of 1 to b of the same integrand, of course. And what is the antiderivative for x to the negative 2? We think of it as a power function. And the answer will be 1 exponent higher, so x to the negative 1 divided by negative 1 from 1 to b. So this will be the limit as b tends to positive infinity, sorry about this, of negative b to the negative 1. And then we get minus minus, which gives us plus 1 to the negative 1. And of course, b to the negative 1 tends to 0 as b tends to infinity. And so the final answer here is 1. So our improper integral is equal to 1. So now we can proceed with our problems of the week for our calculus 3 course. And the first problem is the following. So this is a worksheet. It is find and classify the critical points of f of xy equals x squared plus y to the fourth minus 2xy plus 1. I'm not sure why we insert this plus 1. It's completely irrelevant. But in any case, let's solve the problem in its current form without complaining. So what we need to do is find the critical points. And we find the critical points by taking the partial derivatives and setting them equal to 0. So we will have 2x minus 2y, and f sub y will be 4y cubed minus 2x. So if we set this equal to 0, the first one will give us x equals y. And then for the second one, all we need to do is just plug in. Either thing will give us exactly the same thing. So let's say we plug in y equals x. So we get 4x cubed minus 2x is equal to 0. And if we factorize 2x, that will give us 2x squared minus 1 equals 0. So overall, we're going to get x is equal to 0, x is equal to 1 over square root of 2, and x is equal to negative 1 over square root of 2. And obviously, this is going to yield 3 points. Remember that x is y, so 0, 0, 1 over square root of 2, 1 over square root of 2, and negative 1 over square root of 2, negative 1 over square root of 2. So in order to classify these critical points, we need to take the determinant of the second partial derivative. So let's find them. fxx is equal to 2. Fxy is equal to negative 2. And fyy is equal to 12 y squared. Okay, so let's start with the point 0, 0. So for 0, 0, we have that the determinant is going to be 2, 0 here for fyy, and then negative 2 and negative 2, which is going to give us minus 4, which is less than 0, and this means that this is a saddle point. For 1 over square root of 2, 1 over square root of 2, d is going to be, so again we have the two constant parts, so this is going to be 2, negative 2 and negative 2. These things do not change. And then 1 over square root of 2 square is 1/2. 12 times 1/2 is 6. So this is going to give us 12 minus 4, also known as 8, which is greater than 0. That tells us right away that we do have a local extremum here. And exactly because fxx at 1 over square root of 2 and 1 over square root of 2 is 2, which is greater than 0, this will be a local minimum. Okay, you can always remember that second derivative greater than 0 means concavity or concave up, which is, I'm sorry, convexity or concave up, which is the shape of a smile, and that is a local minimum. And how about negative 1 over square root of 2? So everything will be pretty much identical, right? Because the second partial derivative has this y squared, so nothing will change for this point. And of course, the same kind of reasoning shows us that this point is also a point of local mean. Okay, and that's it with this problem. Then let's go to our next problem, which is an optimization over a compact domain. So let's see what the problem is. So we have find the minimum and the maximum of f of xy equal to x squared plus 2x minus 2y on a rectangle pretty much. So we have, these are usually, I'm sorry, it's not a rectangle. So y is between x squared and 4. And x is between -2 and 2. Let's sketch it so that we can understand what this domain looks like. So if we sketch y equals x squared, or something that resembles with that, and we have the number 2 and the number -2 here, then we see that the lower boundary is x squared, the upper boundary is 4, which is precisely the output at -2 and 2. And so we understand that this is our domain. So this is the domain D. Okay, so the first order of business here is to find if we have any critical points on in the interior. And first of all, it's also a good idea to form a table from the very beginning where we're going to put all the candidates. Of course, since this is a compact domain, the minimum and the maximum are guaranteed to exist, and they will be either at critical points in the interior or at points of interest on the boundary. We will have to parameterize the boundary. We'll come to this in a second. Let's begin with the critical points in the interior, if there are any. So f sub x will be 2x my plus 2, and f sub y will be equal to -2. And of course, once you see -2, you know that there are not going to be any critical points because the second derivative can never be 0. So no critical points. And then let's proceed with the boundary. So the boundary pretty much consists of 2 components. So let's see. So we have this parabolic part, and then we have this line segment. Let's work separately with each one of them. So let's start with the line segment. So line segment from -2, 4 to 2, 4. So here we need to parameterize it, and maybe the easiest parameterization that we could do here is to just think of it as t, 4 for t running between -2 and 2. There are different parameterizations. We could also do 1 minus t times the first point plus t times the second point, which would give a slightly different parameterization. But this is good enough. If we plug it into our function, so we consider a function of one variable, that's the idea, to restrict the function on the boundary to one variable. So f of t comma 4, which is going to be, what is our function? T squared plus 2t minus 4. Okay, so let's find its derivative. So we will have 2t plus 2 and set it equal to 0. That will give us t equals -1. And we have to ask if -1 is in this interval. And the answer is yes. What other points should we consider? As usual for functions of one variable, we also take the endpoints. And the important thing to understand is that we cannot leave them like this. We cannot put them on our table as -1, -2, and 2. We need to translate them to points on the plane. And to do that, we just go back to our parameterization. So this corresponds to the point -1, 4. This corresponds to the point -2, 4. And this corresponds to the point 2, 4. Okay, so these are the first candidates on the table for extrema. So we have -1, 4, -2, 4, and 2, 4. Okay, and secondly, we have what we designated with green. So let's change to green color now. And let's look at the parabola part. From -2, 4 to 2, 4. So here we're going to use the graph parameterization. So R of t is t comma t squared. And t will run from -2 to 2. G of t is going to be f of t comma t squared, which is going to be what? Again, let's recall what our function is. It's x squared plus 2x minus 2y. So this will give us t squared plus 2t minus 2t squared. Okay? So let's simplify this. This is the same thing as minus t squared plus 2t. And let's find its derivative. And its derivative is -2t plus 2. And if we set it equal to 0, we get t equals 1. Okay? Again, we have the endpoint. So these are all the points of interest. And by the way, t equals 1 makes perfect sense because it's within our interval. Again, we shouldn't leave them like that. We should translate them to points on the parabola. And we do that by using the parameterization. So that corresponds to the point 1, 1. This corresponds to the point -2, 4. And this corresponds to the point 2, 4. Please note that the two last points have already been considered. And this is quite common. The points on the boundary will, the endpoints of each boundary component will appear more than once in this consideration. So the only thing that we should add to our table is 1, 1. And so we have 4 candidate points for the extrema. And what we need to do is plug them into our function, the one we want to minimize and maximize. So if we plug in -1, 4, what do we get? We get 1 minus 2 is -1, minus 8 is -9. Then if we plug in -2, 4, we get 4 minus 4, that's 0, minus 8. Then if we plug in 2, we're going to get 4 plus 4 is 8, minus 8 is 0. And if we plug in 1, we will get simply 1. So what is this largest? The largest is at 1, 1, so that's the maximum right here. And we see the input and the output. And the minimum is at negative 1, 4, which is equal to negative 9. Okay, great. Now let's proceed with some problems on Lagrange multipliers. So we have the third problem, which is to find the minimum and the maximum of f of xy equal to x plus 3y on the ellipse x squared plus 4y squared is equal to 13. Okay, we recall here that we need to first of all define a function that describes our constraints. So we define g of xy to be x squared plus 4y squared minus 13. And then the system that we need to consider is that the gradient of f is lambda times the gradient of g, and g is equal to 0. So this gives us 1, comma 3. That's the gradient of f. Should be equal to lambda times 2x, comma 8y. And x squared plus 4y squared should be equal to 13. Again, let's break down this system into simpler equations. So 1 is equal to 2 lambda x, and 3 is equal to 8 lambda y, and x squared plus 4y squared is equal to 13. Now, here things are rather simple. Notice that the first two equations imply that x cannot be 0. If it were 0, you would get 1 is equal to 0. Y cannot be 0, and lambda cannot be 0, which means that we can take these two first equations and divide them by parts. You need to ensure that that you have non-zero numbers, especially the denominators have to be non-zero. The numerators do not matter. But here we have this nice cancellation, and then 1 and 4, and eventually that will give us that x is equal to 4/3 y. Okay, so if we know that x is equal to 4/3 y, then we plug it into the constraint, and that will give us 16/9 times y squared plus 4y squared is equal to 13. Let's see if the numbers are even remotely favorable for us here. I don't think so. So this will give us 16y squared over 9 plus 36y squared over 9 is equal to 13. And overall, this will give us 52y squared is equal to 117. Which, okay, let's see if Let's see if there's any. Yeah, so I guess before rushing to um, simplify things here, we could have done, so we have 9 times 13. Notice that 52 is equal to 4 times 13. So this simplifies to 4 y squared is equal to 9, and y squared is equal to 9 over 4, and y is equal to plus or minus 3 halves. Okay, so we have this nice little simplification. If y is equal to 3 halves, then x is going to be equal to 4/3 times 3 halves, which is equal to 2. And if y is equal to negative 3 halves, then x is going to be equal to negative 2. So overall, we get 2 points. So we get the point 2 comma 3 halves, and we get the point negative 2 comma negative 3 halves. So the idea is now that we could put these points on a table because we are over a compact domain. So the minimum and the maximum are guaranteed to exist. And we have 2 comma 3 halves and negative 2 comma negative 3 halves. And we plug them into our objective function, which is x plus 3y. And we find 2 plus 9 halves, which is 4 over 2 plus 9 halves. That's 13 over 2. And here we get negative 13 over 2. And that will give us the maximum. And this will give us the min. And that's all. Let's now go to problem number 4. Problem number 4 is another problem with the Lagrange multipliers. This time, the objective function is xy, and the ellipse is x squared plus 2y squared is equal to 4. So, for the solution, again, we have to define a function for the underlying constraint. So, we define a g of xy to be x squared plus 2y squared minus 4. And the system becomes gradient of f is lambda times the gradient of g, and g should be 0. Again, this can be written as y comma x, that's the gradient of f. Remember, you keep each of the variables constant when you differentiate with each variable. And lambda times 2x comma 4y, and x squared plus 2y squared is equal to 4. Again, this becomes much simpler as y is equal to 2 lambda x, and x is equal to 4 lambda y, and x squared plus 2y squared is equal to 4. So here again, we have a simple reasoning that x cannot be 0. Why can't x be 0? If x were 0, then the first equation would imply that y is 0, and they cannot be both 0 because they could never fit the constraint. And y cannot be 0 for the same reason. Now we use the second equation. Finally, lambda cannot be 0 because, again, it would imply, so let's write it here, any of these three conditions or rather, if any of these were 0, then both x and y would be 0, which is impossible. And it's impossible because of the constraint. Okay, so again, what we have here is that we can divide the first and the second equation. And we have a lot of pleasant cancellations. So basically we have 2y squared is equal to x squared. Once we know this, then we can replace 2y squared by x squared. So in the constraint, so we get x squared plus x squared is equal to 4. 2x squared is equal to 4. X squared is equal to 2. And x is equal to plus or minus square root of 2. So if x is equal to square root of 2, we go back to the constraint. And that gives us square root of 2 squared, which is 2, plus 2y squared is equal to 4, which gives us 2y squared is equal to 2, which gives us y squared is equal to 1, which means that a y is plus or minus 1. So this yields 2 points, square root of 2 comma 1, and square root of 2 comma negative 1. And if x is equal to negative square root of 2, exactly the same process will give y equals 1 and y equals negative 1, so we get 2 more critical points. So negative square root of 2 comma 1 and negative square root of 2 negative 1. So all in all, we put them on our table and we get square root of 2 comma 1, square root of 2 comma negative 1, negative square root of 2, comma 1, and negative square root of 2 comma negative 1. So that will give us square root of 2, negative square root of 2, negative square root of 2, and square root of 2. So this is a maximum. This is another maximum. So we have 2 maxima on this domain and 2 minima. Or the domain is the ellipse. Okay. Okay. And we have one more problem to go. We recall that the method of Lagrange multipliers gives us critical points. And of course, in each of the problems that we have already solved, we match that to the fact that the domain is compact. So in the last problem, we have f of xy equals to x squared minus y. And we want to minimize and maximize this on the unit circle. So what we do is we define a function that gives us the constraint. So we define g of xy to be x squared plus y squared minus 1. And the system is, the gradient of f is lambda times the gradient of g, and g should be equal to 0. Okay, so this becomes 2x comma negative 1 should be equal to 2x comma 2y. And x squared plus y squared should be equal to 1. So, I'm sorry, there's a lambda here. So, this translates to 2x is equal to 2 lambda x, and negative 1 is equal to 2y, 2 lambda y, and x squared plus y squared is equal to 1. Now, here we do something slightly different. We start with the first equation, and we start by dividing both sides by 2, and then bringing over to the left-hand side and factorizing, and this gives us 2 cases. So x is 0 or lambda is 1. Now, one of the two has to hold. If x is equal to 0, we go directly into the constraint and we get y squared is equal to 1, which means that y is equal to plus or minus 1. That yields 2 points, 0, 1, and 0, -1. So these are two critical points. On the other hand, if lambda is 1, then we go into the second equation, which gives us -1 is equal to 2y, which means that y is equal to -1/2. And if y is equal to -1/2, then we go again into our constraint that gives us x squared plus 1/4 is equal to 1, or x squared is equal to 3/4, or x is equal to square root of 3 over 2 with a plus or minus. So that gives us two more points, in particular square root of 3 over 2 comma -1/2, and negative square root of 3 over 2 comma -1/2. Okay, so our minimum and maximum is guaranteed to exist, and we're going to put all this on a nice table and see which one is which. So first of all, the critical points that we found are 0, 1, 0, -1, square root of 3 over 2 comma -1/2, and negative square root of 3 over 2 comma -1/2. Now, let's plug them into our function. What was our function? It was x squared minus y. So this will give us -1. This will give us 1. X squared for square root of 3 over 2 will give us 3/4. 3/4 plus 1/2 is the same thing as 3/4 plus 2/4. So that's 5 over 4. And we're also going to get 5 over 4 right here. So overall, we see that we get our minimum right here, our maximum here, and there's a second point of maximum right here. And please notice that the point 0, -1 is neither. So, and that's it's good to remember that the method of Lagrange multipliers does not give directly minima and maxima, it gives critical points. And of course, we got 4 critical points. One of them was a minimum, 2 of them were maxima, and the other was neither. And that's all. That concludes the solution of the fifth problem and concludes the solution of the solutions of the full set of the weekly worksheet and also the review. Okay, thanks for watching.